Chapter 9.9, we're going to talk about representing functions as power series. So we're going to start off talking about these geometric series. We've talked about them in the past. We just want to kind of refresh our memory. So if I have a geometric series, I got 2 plus 6 plus 18 plus 54. This is the a sub 1, so the first I wrote that wrong. That should be a 2. So a sub 1 is 2 here. That's the first term, and r is 3. So the series would look like this. We know that this series would diverge by the geometric series test because our r is greater than 1. Right? If we change that though and made r 1/3, then this series would look like this. We know this would converge by the geometric series test because r is less than 1. And not only that, but because it's a geometric series, we could also talk about what it converges to. Right? It converges to the sum of a geometric series is going to be a sub 1 over 1 minus r. So here that is 2 over 1 minus 1/3, which is 2 over 2/3. So this sum would converge to 3. Right? And you can play around with that by plugging these in your calculator and taking a look at it, and it gets very, very close to 3 as we increase the number of terms. So now let's take a look at, let's make a sub 1 1 and r, make that equal to x. And the series would look like this. Right? So it's 1 times x, 1 plus x squared plus x cubed plus x to the 4th, and the summation notation would look like this. It would be x to the n. Right? So that's going to converge to this sum, 1 over 1 minus x, but only for specific values of r, right? In this case, x. Only if x is less than 1 does this series converge. Otherwise, the higher power of x we have, the bigger that term is going to be, and we're going to diverge anyway, right? So to get this kind of a sum from this series, we have to have x less than 1. All right, so we can represent different functions as a power series by using this idea of a geometric series. All right, so another way of saying exactly what we said above, we kind of worked at it from the other direction, but here we can say if we want to represent some function 1 over 1 minus x as an infinite sum, we can write it as a power series, and here's the infinite series that would represent that function. All right. So because x has to be less than 1, or really truly the absolute value, earlier when I was talking about the r, it was really the absolute value of r that had to be less than 1, right? So the absolute value of x has to be less than 1. So basically we have this 1 over 1 minus x centered at x equals 0, and the interval of convergence is an open interval from -1 to 1. Right? If we want to represent some other function as a power series, we can try to rewrite them in this form. So notice it has a very specific structure to it. We have a, we have a in the numerator. The denominator is going to be 1 minus our r. Right? If we want to represent f of x in another interval, we need a different series for it. We can't represent the same series. A function in a different interval with the same series. We'll need another series for it. So let's take a few examples and work through them.